Okay, so we have reduced our two body problem to a one body problem of mass mu, a particle of mass mu that is moving around in a central potential given by u of r. Okay, and we have not yet specified what u is, other than that this is a central force field. Okay, now this looks like a problem of 3 degrees of freedom. Okay, so we have gone from 6 degrees of freedom to 3 degrees of freedom, and because your r is now x, y, z coordinates, okay, x, y and z, and you know what r was, that's the separation between the two particles, m1 with masses m1 and m2. Now you may ask, where is r equal to 0? Okay, where is the origin of your potential field? Where is the center of the force field? Okay, that's easy to find out where it is. Let's recall what were the expressions which were relating r1 and r2 to capital R and small r. If you recall, we had r1 to be, this was the center of mass, radius vector for the center of mass, and then you had this piece, right? And for r2 you had the corresponding thing. Here it was, instead of 2 you had 1 here. Okay, otherwise it was the same thing. So clearly, if you put small r to be 0, r1 and r2 both become capital R. Okay, so that is the location of the center of mass. So your r equal to 0 corresponds to your both the particles being situated at the center of mass. So that place, the center of mass, is where your r is equal to 0. Okay, so that's fine. Now let's go back to our discussion of that Lagrangian which you have written down. Okay, and I was saying that let's ask whether these are the best coordinates to use, the x, y, z, and clearly they are not, because your system has a spherical symmetry, so you would like to use more suited coordinates here. Okay, so first point to note before we can make some progress is that because we have a central field, okay, meaning it does not, the only radial separation matters. Okay, maybe I should make this point that often I would be switching back and forth between the interpretation of the two body system as one body system, which is given here as the Lagrangian right now, but sometimes I'll be making statements which will pertain to a picture where really those two bodies are present. Okay, so I hope it will not be a issue in understanding. Anyhow, so because our potential energy is dependent only on the coordinate small r, only the magnitude of it, it does not matter at what azimuthal or polar angle that that point mu is located. Okay, meaning if I take my system and rotate it by some amount about some axis, okay, then that that will appear as a cyclic coordinate. You know that is the symmetry of the system. And because you know there are three independent directions, let's say three mutually perpendicular directions about which you can do independent rotations, okay, you will have correspondingly three conserved quantities, three conserved angular momentum, which are Lx, Ly, and Lz. Okay, this is what we discussed very much in the beginning of this course. So let me write it down here. The dynamics is not affected at all if the system as a whole is rotated. About some axis. Okay. Now, as I said, because you have three directions, mutually perpendicular directions you can take, this will imply that there are three angular momenta which are conserved, which are Lx, Ly, and Lz. Okay, or equivalently, I can put it as a vector equation and say that L is equal to constant. Okay, this will be a constant of motion. So whatever your system does, L will remain unchanged. Okay, so this is what the symmetry implies. But of course, this will not tell, whatever information is given to you cannot tell what the value of this vector L would be. Okay, so L cannot be determined from whatever we have talked till now, because that is going to be determined by the initial conditions or by how you prepare your system. Okay, so L is determined by the initial conditions. I hope this is clear. Okay, which is same as saying how you prepare your system. I'll give you a simple example to understand this. So you have your, so let's look at the two body problem. So let's think of both the particles M1 and M2 are there in front of you. Okay, and let's say particle number M1 is located at some place, and you take particle number 2, which interacts with particle number 1 via central force, meaning the forces depend only on the separation. Okay, and you take particle number 2 and fire it directly towards particle number 1. Okay, now if you do so, the angular momentum would be 0. Okay, this you should be able to immediately realize, okay, just by from the definition of angular momentum, that the angular momentum about the center of mass, or about r equal to 0, okay, this will be 0, this of this system. This particle will be falling or going towards directly the particle number 1. So I prepared my system such that the angular momentum is 0. Now I could fire particle number 2 at some angle, okay, rather than making it directly go towards M1. I can fire it at some angle and give it some velocity. Okay, and that way I can change the direction and the magnitude of the angular momentum which the system is going to have. Okay, so your L is controlled by the initial conditions. Okay, so let me just write down here what I said. Example, if you fire M1 towards M2, then your vector L would be 0. Okay, that's fine. Let's see what else I want to say. Okay. Now let's go back to our Lagrangian here. Okay, and try to see what good coordinate I can use. Now the moment I say, okay, there is an angular momentum of the system, now I have a direction in the problem. Okay, the direction of L, okay, now we have direction in the problem. So till now in the discussion I was always saying the potential is spherically symmetric, and of course clearly there are no directions, but now we realize that okay, there is a direction in the problem, and that is given by the angular momentum. Okay, and let's see how I can utilize this to make further remarks about this statement. Okay, so I found a direction to the problem, and this is clearly your L is R cross P. Okay, and this R is measured from the origin, and you know where the origin is, so angular momentum is measured with respect to that point. Now this equation says that because this is constant for my system, okay, this I have already established here based on the symmetry of the problem. This says something nice. First of all, you observe that because L is not going to change with time, okay, its direction is not going to change with time, neither its magnitude. Both the things will be constant. So let me write down direction of L constant, and magnitude of L is also constant. Okay, so let's see what we can say from the fact that the direction is constant. So because this is a cross product, okay, you know that L is perpendicular to R, or R is perpendicular to L, either way, which means the particle of mass mu is moving in a plane that is perpendicular to L, right? See, the R has to be always perpendicular to L, which means the R is confined to a plane perpendicular to L, and of course it has to have also a momentum within that plane. So what I have been able to show is that because the direction is constant of L, my symmetry dictates that the motion will happen in a plane. So these two particles, okay, will always remain in a plane. Okay, so this is what our conclusion is. Constancy of direction of L implies motion happens in a plane. Okay, and the reason, as I said, because R and L have to be perpendicular. And that's because of the cross product definition. Okay, that's nice. What if L is equal to 0? Then I do not have a direction because L is 0. In this case, my R cross P is 0, and that will happen to be 0 only if r and p are in the same direction, right? If that is the case, then this cross product will vanish and your particle is this this is moving in a straight line. Or equivalently, the two masses are directly falling into each other, or just getting separated from each other along a straight line. That is what I said a few moments ago. Okay. Let me write it down. So R is parallel to P. So your mu is moving in a straight line. Or for our, the picture of both the bodies are present, for that it will mean that M1 and M2 are going towards each other this way or that way, okay, along a straight line. Okay, that's good. Okay, so this is good. So now that I have established that the motion is happening in a plane, I would like to write down my Lagrangian, which was here, using this fact. So let me write down. L is half mu r dot square minus u of r. Now I know the particle is in the plane. You can say that I will align my z-axis with the direction of L, okay, and the plane in which the motion is going to happen would be a xy plane. So that's one choice we can, that's the choice we can make without any loss of generality. I can just choose z direction to be the direction of L. So I will say that. So choose z-axis to be along L, okay, and the motion happens then xy plane. Okay, fair, that's good. Now I can write down this kinetic term, half mu r dot square, in the xy plane and using polar coordinates, because that will be useful. You have radial symmetry here, so instead of using Cartesian coordinates x and y, it makes sense to use the polar coordinates. So this becomes half mu r dot square, let me put a vector here, r dot square plus half mu, okay, r square theta dot square, and then you have the potential term here. Okay, that's fine. So my Lagrangian now is I should have anyway, let me write it down again. Half mu r dot square plus half mu r square theta dot square minus u of r. Okay, this r is just the radial distance. It's no more a vector because we also have theta now, and this is the Lagrangian. And we should always look whether something is cyclic here, and indeed it is. You see that theta does not appear anywhere. The r does appear, of course, everywhere, but theta does not, which means theta is cyclic, and which further means that the momentum conjugate to theta would be conserved. And you know, theta is the polar angle, so there is nothing polar, it's all in the plane, so it's the angle, so it means that the corresponding angular momentum will be conserved, which is you can find p theta, which is del L over del theta dot, which you already know that it is angular momentum. You get taking the derivative mu r square theta dot, and this is a constant. Okay, and that constant is of course going to be determined by your initial conditions. Okay, and let's call that L. Okay, and you can clearly see that this is just the angular momentum of your system, right? The magnitude of capital L, magnitude of this L here. Okay, so you have got a first integral here which involves only one derivative. Okay, and this is what you expected. You would have gotten anyway the a conserved quantity here, and this small l is determined by the initial conditions as we discussed some time back. Okay, now let's make some. Before I do that, let me just write here that this implies that theta dot is equal to L over mu r square. So I have solved, not really, because it's still r is still present there, but anyway I have such a relation now. Now I want to make a quick interpretation of what I have got. Okay, what this condition of conservation of angular momentum here in terms of this expression implies. So I'll what happened? Okay. Okay, I need to add some. Yeah, we have some place, so why? Okay. So I'm looking for a geometrical interpretation . Angular momentum conservation. Okay, so I want to see what it would geometrically mean if someone tells me that you have a center force problem and your angular momentum is conserved, the motion is happening in one plane. Okay, all this would amount to what geometrical feature of the problem. So let's say this is the origin of my radial coordinate, this small r, and this is this plane of the screen is the plane in which the motion is happening, and your particle mu is moving in some way. At some point it's here, and this is the radial coordinate, so this is the radius vector r. After some small infinitesimal time t, dt, what happened? It moves here and it covers an angle d theta. Okay, let me drop a perpendicular here, and this arc length is, so this is r, this it's r the radius vector. This is r d theta. Okay, and if you find out the area of this infinitesimal this sector, you see if this is infinitesimal, so this area which you are seeing here is this. Half r into r d theta. Okay, that's the area of the triangle or the sector which coincide when your angle is infinitesimal. And if I calculate dA over dt, all I have to do is divide both sides with dt, I get half r square theta dot. So this is the area, the rate at which, so this quantity is the rate at which the radius vector sweeps the area. Okay, so in a, I mean, when this vector is moving, okay, this particle is moving, the radius vector is moving, it's sweeping some area, and this gives the rate at which that area is swept. Let's see what our angular momentum conservation implies about this rate of this dA over dt. Okay, so here I had found theta dot to be L over mu r square. Okay, so theta dot was L, which is a constant, over mu r square. If I substitute in dA over dt, I get dA over dt to be half r square, and theta dot is L over mu r square, and the r dependence goes away, it cancels, and you have half L over mu, which is a constant. Okay, so what it says is that the amount of area that the radius vector is going to sweep in some time interval, okay, is same as it would do at any later time if you take again equal time interval. Okay, so if you take I mean, I can write it this way, dA is this constant which you have found, half L over mu into dt. Okay, so area in equal times, in equal time intervals, the radius vector sweeps equal areas. Okay, that's nice. We have determined this, which is the famous Kepler's second law. Okay, this Kepler's second law we have determined based only on the fact that angular momentum is conserved and the forces are central in this case, in this discussion. Beyond that, I have not used anything. Okay, so just to summarize before we move next, we have found two things. Motion happens in a plane, and we have found Kepler's second law holds true. Okay, these two things, and I have assumed nothing more than the fact that I am using central forces. Okay, now let's look at the equations of motion.